Hello and welcome to session number 9. In this session we're going to introduce a new topic, capacitance. We'll be looking at the parallel plate capacitor and the spherical capacitor. We'll be finding the capacitance of the Earth, and then we'll be shifting gears a little bit and look at compensated doping, and hopefully we'll get to be able to, towards the end, look at the resistivity of compensated gallium arsenide and silicon. But first, the finale to Franz Joseph Haydn's trumpet concerto in a marvelous performance, Alison Balsam. Let's enjoy. Okay, so let's jump right in, and we're going to first take a look at some energy band diagrams just to make sure that we're comfortable with the different positions of the Fermi level. And here we go with that. Okay, see if we can identify the following energy band diagrams and estimate the doping levels. Well, take a look at this guy over here. We note that the Fermi level is just above intrinsic, so I would say that that's lightly doped N. Here, the Fermi level is way above intrinsic. Just remind ourselves, I didn't label these, I probably should. This is the conduction band, this is the valence band. So here we're well above intrinsic, which is right in the middle. So this would be moderately to heavily doped N-type. This is degenerately doped N-type because the Fermi level is right at the conduction band edge. Here we're slightly below intrinsic. Intrinsic is maybe just a little bit above that. So this would be very lightly doped P-type. It's kind of the analog of the lightly doped N-type, heavily doped P-type, and intrinsically doped P-type. Okay, so hopefully that's not very challenging. And let's go on to capacitance. So when we look at capacitance, first thing I want to do is have a comparison between Newton's law and Coulomb's law. This is Newton's law, the attraction of masses, which is square law, and this is Coulomb's law, the attraction or repulsion of charge, and it looks exactly the same. Well, there's certainly similarities. They're both square law, inverse square law, I should say. The force of attraction of masses is inversely proportional to distance squared. The force of attraction of charges or repulsion of charges inversely proportional to the distance squared. The difference is in this constant G and this constant K. What is the constant G? Well, from our previous discussions, we could say it's just to make the units come out, and that's right. Although it's a little bit more deep than that. This is called the universal gravitational constant, and it's one of the basic constants of nature. The other two, I'm not a cosmologist, but I believe the other two are Planck's constant and the velocity of light, speed of light. It is not a material constant. K, on the other hand, the constant in Coulomb's law, is a material constant. It depends on the materials between the charges. The universal gravitational constant does not depend on the material between the two masses. And the other thing that we mentioned briefly also is that here masses always attract. Here charges can repel or they can attract. I guess you could say if we have antimatter, perhaps they could repel. I'm not really sure how that goes. Okay, anyway. So G is called the universal gravitational constant. The units of force, we've seen a number of times, kilograms, meters divided by seconds squared, because F equals ma. The units of the universal gravitational constant work out to be meters cubed divided by seconds squared kilogram. And you can see that the kilograms on the bottom because force has kilograms on top, and we divide through by kilograms squared. So that's why that's what happens. Okay, now what I'd like to do then is to go back to this thing and separate out the M2. Just pull it out of the equation, and what's left over is G m1 divided by r squared. And let's take a look at the attraction of any mass. Could be you, me, moon, a air molecule, anything. Doesn't matter what it is, but it's close to or not too far away from the surface of the Earth. So the r squared is more or less constant. So we want to take a look again at the traction of the Earth to some mass which is close to the Earth. So I have the universal gravitational constant, I have the mass of the Earth, I have the radius squared of the Earth. So we put all those things in, and we find this is the mass of the Earth. I'm sorry, this is the universal gravitational constant. This is the mass of the Earth in kilograms. This is the radius of the Earth in meters. And I find 9.8 times divided by second squared, 9.8 meters per second squared. And I round up to 10, and that is units of acceleration. And that is, in fact, what we were using in session 2. In fact, we could have done this in session 2. So we're tempted to say that the units of all of this stuff here, without the Q2, pulling the Q2 out, that all this stuff would be units of acceleration, simply by making an analogy between the force between two charges and the force between two masses. That is not correct. In fact, this thing here is units of electric field. This is units of force. And we can motivate that from its, I guess you could say, kissing cousin, which is Gauss's law. Now, we're not going to derive Gauss's law. It's generally done in field theory. We talk a lot about it. But we're going to use Gauss's law to try to get a feel for the units of, specifically of this thing called K. Okay, so again, we're not going to derive Gauss's law, but let's use it. What it does is it relates the electric field to charge. And that makes sense. Whenever there's a charge, that charge produces an electric force. Whenever there is a mass, the mass produces a gravitational force. That is completely analogous. There is a constant which we kind of stick in, which makes the units come out. Here in Coulomb's law, we just called it K. Now we're going to call it something else. It's a material constant, and that's kind of important, which we'll show in a little bit. Here we're going to call it the permittivity. Let's look at how we would use Gauss's law. Here we have a charge. It could be a charged sphere. It could be a charged point charge. Doesn't matter. It's spherically symmetric. And from that charge emanate lines of electric force. And here are those lines shown here. There's a certain density. There's a lot more of them. We don't know how many. It's the absolute number is not important. The important thing is how many lines are cut by an element of area dA. And what Gauss's law says is we take all those lines of force and we add them all up around a closed surface. That's this little oval here, ellipse here. And when we do that and multiply by the permittivity, we get the charge. Okay, well, let's do it. The unit of area dA is perpendicular to the surface. It's a vector. In this case, it points out. This rather intimidating dot here in the middle means it's the dot product. If the electric field and the area are perpendicular, the dot product is 0. If they are parallel, the dot product is 1. It's simply the product. In this case, they are always parallel because the element on the surface points out, the electric field points out. So this is just the multiplying of the electric field by the element of area dA. And since the electric field is constant across around a sphere, we can pull the E out, which we do someplace right here. we pull the E out of the integral, and we just have the surface area of a sphere. And the surface area of a sphere is 4 pi r squared. And Gauss's law says that epsilon multiplied by the electric field at the surface multiplied by 4 pi r squared is equal to Q. And we find the electric field is Q divided by 4 pi epsilon r squared. That's just Coulomb's law, where K is 1 over 4 pi epsilon. So we've essentially taken Gauss's law and we have pulled out of it essentially Coulomb's law, which gives us some confidence, at least, that Gauss's law has some degree of validity. The important thing about Gauss's law is, here it is, going to be someplace, is that it relates two quantities which I feel should be related intuitively, charge and electric field, and it tells us how they are related quantitatively. And whenever we have a quantitative relationship, we better have the units come out right, so epsilon makes the units come out correctly. Okay, so the next thing we're going to look at is the parallel plate capacitor, and then we'll go back to the spherical capacitor when we find the capacitance of the Earth. So let's consider this particular structure. We have a voltage, positive charge, positive electrode, which is the big, the larger line here, positive charge on the left side, negative charge on the right side, two parallel plates separated by a distance d. Now, Gauss's law tells us, and intuition tells us, that whenever there's a charge, there is an electric field. So we expect to have an electric field between the two electrodes in the space d. In fact, Gauss's law tells us what that relationship is. This perhaps should be a double integral, but the point is that it is the integral of the electric field dotted with the area is equal to the charge divided by epsilon. In this case, the area points from left to right. It is parallel to E, which also points from left to right. So this is just the product. Now, we want a circuits representation. Well, there are very few electric field meters. Electric field is not generally the thing that we measure. It's rather voltage, but voltage and electric field are related to one another very intimately. If we have the electric field with units of electric field are volts per meter, I multiply by the distance, I get the voltage. So Q is related to E, therefore Q is related to the voltage. The constant of proportionality between the charge and the voltage we call it C. And as this was explained to me when I was taking the course, this goes back a few years, that one of the mnemonics to remember this, I'm not suggesting that this is the right mnemonic, but in those days Q stood for something that was queer, so the professor said the queer stands alone. Perhaps today that's not what we would use, but you can think of another mnemonic. But the bottom line is that Q is equal to the capacitance multiplied by the voltage. Okay, so here is a more complete representation of that. We have the charge positive on the left side, negative charge on the right side, and we have lines of electric field. In this case, there are 8 of them between the positive and the negative charge. Now note the direction of the arrow. We'll have a lot more to say about that a little bit later on. It works out, that's one of those things we have to just get used to, that the arrow of the electric field always points away from positive charge. It is the direction that a positive charge would move if it's in this electric field. So if we have a positive charge sitting right over here, which way is it going to move? Well, it's going to be repulsed by the positive charge on the plate, and it's going to move from left to right, the direction of the arrow. Now let's place a imaginary area between the electrodes, and if we want to find out what the magnitude of the electric field, we just count the number of lines. In this case, there are 8 lines. It doesn't give us the absolute magnitude of the electric field, but as this, and this is represented by the little red arrow here, as the area moves from left to right, it tells us how the electric field changes by looking at the number of lines that are cut. In this case, if this imaginary field was right on the left side, it would cut 8 lines. If it's on the right side, it would cut 8 lines. So the magnitude of the electric field doesn't change as we go from left to right. However, if this area, this imaginary area, was in the plate to the left of the plate, how many lines is it cut? 0. So that there are no lines cut. The electric field would be 0. Left of the plate, there are no lines cut. To the right of the right plate, so the electric field would be 0 in this region right here. Okay, so now let's take this distance and double it. Well, if the distance doubles, what happens to the electric field? D goes up by 2. The voltage is constant, so the electric field must decrease by a factor of 2. And therefore, the capacitance must be proportional to 1 divided by D. And we can see that right here. V is constant. Electric field goes down by a factor of 2, which means that Q goes down by a factor of 2, which means that C goes down by a factor of Q. Ooh, that's a lot to remember, but you can follow the logic, and hopefully it's not too obtuse. We can also see that here. If we look here, and we double the radius of the sphere, since the electric field, someplace, where is it? The electric field is proportional to 1 over r squared. If we double r squared, the electric force goes down by a factor of 4, but the area goes up by a factor of 4 because the area is proportional to the radius squared. So doubling r doubles the area by 4, reduces the electric field by a factor of 4, and the charge stays the same. That's exactly what we'd expect because we haven't changed the charge at all. In our case here, we've doubled the distance, and the voltage is constant, not the charge. The charge adjusts itself to give a constant voltage. So if we double the distance, the charge goes down by a factor of 2, the electric field goes down by a factor of 2, the capacitance goes down by a factor of 2. Capacitance is proportional to 1 divided by the distance. Okay, so now let's double the area of the electrode and see what happens here. And one way we can do that is just to go back to Gauss's law. It's right here. There's E is constant. There's no reason we changed E. The voltage, of course, is constant. The area is now doubled, let's say. What happens to Q? It doubles. Twice as much charge. The density of the line stays the same, which is another way of saying that the electric field stays the same, but there's twice as many to now So in order to have that all work out, the charge Q must double, and if the charge Q doubles with constant voltage, what happens to C? It doubles. So we come to the conclusion, hopefully it's reasonable, that the capacitance is proportional to the area of the electrodes for a parallel plate capacitor, inversely proportional to the distance between them. Okay, so that's the geometric factors. Now, the most interesting of all is the ability of the electric field between the electrodes to separate ever so slightly charges that may or may not be present. Specifically, we're talking about a dielectric which has areas of negative charge and areas of positive charge. When there's no electric field, the negative and the positive come together, they coalesce. However, in an electric field, in this case, for example, the electric arrow is pointing from left to right. It repulses the positive charge, attracts the negative charge. It creates an internal electric field which goes from right to left, opposing the external electric field. The external electric field caused by the voltage between the electrodes. Again, this is the space between the electrodes here. We're assuming that there's a material here which has possibility of separating negative and positive charge. Silicon, for example, there is an electron cloud around the nucleus. The nucleus is positively charged, the electron cloud negatively charged. In the presence of an electric field, the electron cloud moves, I should say, in the case of an electric field, moving from left to right. The negative charge, the electron cloud, will tend to move left. The positive nucleus will tend to move right, producing an internal electric field which opposes the external electric field. Now, Le Chatelier's principle tells us that whenever we stress a structure, the structure will react trying to reduce the stress. And that's exactly what happens here. We have a stress, we have an internal electric field which acts in a way to reduce the electric field. The electric field wants to increase itself to counteract that stress, and it does that, again, by the rather trivial expedient of increasing the Q. The Q can be whatever we want, so if we have an internal electric field which opposes the external electric field, the external electric field would say, hey, this is a stress, I don't want it, I'm going to try to reduce it, I'm going to increase my charge to compensate for this internal electric field. So going back to the equation, Q goes up, V stays constant, C goes up. So we hopefully conclude, and this is the final conclusion, that the capacitance is proportional to the permittivity. The permittivity says how easy it is to separate these charges. We split up the permittivity by a constant. This is the permittivity of free space, and this is the relative permittivity. This depends on the material. So E sub r is a very important parameter. It is 1 for a vacuum or for air or for many gases. It is 4 for glass, which is relatively low. It's approximately 12 for silicon, and many semiconductors also have relative permittivities of about 12. Okay, next big subject is the capacity of the Earth. Okay, so here is the structure for finding the capacitance of the Earth. There are two spheres. There's an inner sphere and an outer sphere. The inner sphere is the radius of the Earth. That's pretty big. It's about 6 kilometers or so. And the outer sphere is an arbitrarily large sphere whose radius is larger than the radius of the Earth. And you notice I made this as a dotted line because we're going to move this in and out. We dump some charge on the Earth, positive charge in this case, and we find that for each positive charge, we have an arrow emanating out and ending on a negative charge. So we have a positive voltage on the Earth and a negative voltage on this imaginary outer sphere. The details of the structure and the calculation are given in the text. I'm just going to give the answer here, the result. And we find that the capacitance is equal to the charge on the Earth, which is equal to the charge on this outer sphere, divided by the voltage, and that is only a function of the structure. It's the radius of the Earth divided by K, where K is this constant in Coulomb's equation, 9 times 10 to the 9th Newton meters squared per C, and we find that the capacitance of the Earth is approximately 700 microfarads. Okay, it's a number. If it was 1,000, it would be less. If it was 1,000 microfarads, it would be 1,000th of a farad. This is less than 1,000th of a farad. Okay, all right, well, let's see what that means. If, however, we allow the outer sphere to end not at infinity, but we collapse it back in, so it's about 5 miles higher or larger than the radius of the Earth. In other words, the radius of the Earth and the outer sphere here is about 5 miles more than that. And 5 miles is a nice number because it's the height of Mount Everest, about the limit of the atmosphere. We find that the capacitance of this structure is about 1 farad. Now, when I was studying this, 1 farad capacitors were really, really large. You could make them. You could hold them in the palm of your hand, but that was about it. The capacitance that we encounter in semiconductor devices are smaller. They are much, much smaller. They're 1/1,000,000th of a microfarad. 1,000th of a microfarad would be a nanofarad. 1,000,000th of a microfarad would be something called a picofarad. Pico refers to 10 to the minus 12th, and it's abbreviated as PF, picofarad. And if you're an engineer, you certainly would know the lingo. We call it a puff. So 1 puff is 10 to the minus 12th farad. Now, if we scale down the dimensions of the inner radius such that it's not of the Earth, but it's only 1 meter, that's still pretty big. It's about 3 feet. And then we let the outer radius go to 1 micron, we find that the capacitance of that structure, we expect it to be huge because the distance between the inner sphere and the outer sphere is only 1 micron. But we find that it's only about 100 farads. Today, there are commercially available capacitors that you can hold in the palm of your hand, which are over 500 farads, and they are called supercapacitors. How is it possible? Well, the trick is not to decrease the distance, but to increase the area by using very porous materials, specifically carbon. Supercapacitors are being made today, and they're commercially available. They're not even expensive. I think they're in the $10 to $20 range for something like 500 farads. They are incredible. And it is supercapacitors combined with the latest technology in batteries, which hopefully will very soon revolutionize our economy and move us from a fossil-based to an electrically-based economy. Tesla bought the premier company in supercapacitors. I believe it's called Maxwell Technology. They were purchased about 6 to 8 months ago. So do your research. Look up supercapacitors. They are our future. And what was previously this kind of impenetrable wall, there were capacitors on one side, there were batteries on the other side. They each had their own properties. Now that wall has been tumbled down, and capacitors and batteries, they still have their differences, but they're coming together to create a kind of unified economy, which is going to be incredibly important. Okay, so now let's look at a graphical derivation of something called Poisson's equation. Okay, we'll start with the previous structure. This, by the way, is in Chapter 7. It's a little bit of a jump ahead, but I think we have the tools to do it. So if we go back and we look at our parallel plate capacitor, we have a voltage between two plates, positive voltage on the left side, negative voltage on the right side. We have lines of electrical force going from positive ending on negative. The electric field in this region is 0. No lines are cut. The electric field on this side is 0. No lines are cut. The electrical field between the plates is constant as we move this imaginary square back and forth, because we're cutting the same number of lines from the left side to the right side. Now, okay, this equation, this figure here just shows the electrical field. It's 0 outside of the capacitor on the left, it's 0 outside the capacitor on the right, and in the middle it is constant, and that's all this shows here. Okay, now suppose we have the following structure. Instead of having a dielectric, we have a dielectric which is split right down the middle. On the left side, we have a density of positive charge, and on the right side, we have a density of negative charges, and those densities are equal. And now we have this movable square right here, and we're going to move the square starting over on the left of the dielectric. The field is 0, and we get to this point, we start cutting some lines. And we cut how many lines? Well, each positive charge has one line emanating from it. 1, 2, 3, 4, 5. So we have a little bit of an electric field. Now we move this thing further in, and now we have double the electric field because we have double the lines cut. And we keep moving it, and we have more lines cut, and we have more lines cut, and we have more lines cut. And as we move it right to the junction, we have the maximum number of lines cut, and that number of lines cut increases linearly until we get to the right side of the junction. We get to the right side of the junction, the lines start to terminate. This guy will terminate here, this guy terminates here, this guy terminates here, etc., etc. So on the right side of the junction, the electric field goes down. And we see that right here. The electric field starts at the left side, increases linearly, and then when we get to the junction, it maxes out, and then it decreases and goes to 0 at the right side of the dielectric. Now consider the following structure. Here we have lots of negative charge, and we just reverse the signs of the charge on the left side, and we have a smaller density of charge on the right side. So here the slope of the line is going to increase very dramatically on the left because we have a very high density. So moving just a little bit gives us a very big increase in electric field, and on the right side, since we have so few charges, we expect the density or the electric field to decrease because the density of charges is so much lower, and that's indicated here. So we conclude that the slope of the electric field, how fast the electric field changes, depends on the density of charge. This row is density of charge, it's not resistivity. Okay, so now let's consider the effect of the permittivity. Remember, the permittivity is the ease in which charge can be separated. So if we have a dielectric, for example, silicon or glass or anything where we can have a negative charge being separated from a positive charge, we have a permittivity, relative permittivity, which is greater than 1. We have fields set up by those little tiny dipoles which resist or in the opposite direction of the external electric field, and therefore the slope of the electric field with respect to x is proportional, in this case, to 1 over the permittivity. So in summarizing, we have dE dx, which is the slope of the electric field with respect to position, is equal to the charge density divided by the permittivity. So the smaller the charge density, the smaller the slope. Here, the slope here is much smaller than on this side, where you have a high charge density, and it's proportional to 1 over the permittivity. And this is Poisson's equation, and it is one of the most useful tools in our tool bag. So I have to tell you a little story here. So I was teaching field theory, I forget where, I've taught at a number of universities. So one of the standard problems that everybody hates in field theory is to find the potential of a charged dielectric sphere in a constant electric field. The reason is because the mathematics gets a little bit nasty. So somebody asked a question in the middle of all of this gunky differential equations. He says, why are we studying? This is the most idiotic thing I ever heard of. I'm never going to use it. This is back before semiconductors were in wide use, and he was right, and yet he was wrong. Every time you turn on a computer, you have a couple of billion, that's billion with a B, charged dielectrics. So I like to call this Poisson's revenge. Poisson's equation is important, and it's a big deal. And charged dielectrics are a big deal. They're a very big deal. Okay, so our last topic, which is relatively advanced, generally not covered in a undergraduate course, but we're going to dive into it because I think we have the tools to do it. It's called compensated doping with shallow traps and deep traps. And why do we want to do this, and what's this all about? Sometimes it's really desirable to artificially create an intrinsic semiconductor. Intrinsic semiconductors generally, except for tin, have very high resistivity. Now, in theory, it should be possible to compensate for donors by having an equal number of acceptors. For example, if I have 10 to the 16th donors, I just put in 10 to the 16th acceptors. 10 to the 16th donors raises the Fermi level to about 0.36 above intrinsic, and then when I put in 10 to the 16th acceptors, the Fermi level falls back to intrinsic, and then I've got intrinsic silicon, for example. The problem is that if I don't get it exactly right, if I'm even off by a few percent, the technique breaks down completely. However, if we use these things called deep traps or deep acceptors, then we can have a situation where the changes very dramatically in the right way. Okay, so let's see how that works. Here we have, for example, I guess I call it the silicon. It could be anything. And we have the electronic state for silicon, which is about 40 or 50 milli electron volts below the conduction band. And instead of using acceptors, which are shallow down here, we use deep acceptors, which basically have their EA, their acceptor level, right at the intrinsic, right in the mid gap. And actually, this should not, if it's silicon, see, I made a mistake the first time. If it's silicon, this would be gold and not chromium. If it's gallium arsenide rather than silicon, yes, this would indeed be chromium. So sorry about that. Not the first time I said something so silly. But anyway, so let's just change this then to gallium arsenide. Okay. Now we can do this graphically. There's a discussion of this in Chapter 4, but that's a little bit beyond our pay grade right now. So this is what we have in gallium arsenide. In gallium arsenide, the band gap is 1.44, 1.45, whatever, and we have the Fermi level sitting right in the middle of the band gap at about 0.72 eV below EC. This is not a line of electric force. This is just says the distance between the conduction band and the E sub A, the chromium acceptor level, is about 1/2 the bandwidth. So now I want to compensate using chromium, which is right smack dab in the middle, and I find that the number of ionized acceptors is equal to the number of acceptors multiplied by the probability that the state is occupied. Well, E sub F is equal to E sub A. So if that's true, then N sub A plus is equal to N sub A simply divided by 2. And the reason is, this is the Fermi function, E sub A or E sub F, they're the same. E sub F and is equal to E sub A, they're the same place, is equal to 1 divided by 1 plus E sub A minus E sub F, which is 0 because it's E sub F minus E sub F, and that's 1/2. So the required doping then is N sub A is 2 times if we're N sub A plus. So if N sub A plus, for example, we have 10 to the 16th donors, shallow donors, we put in 2 times 10 to the 16th of deep acceptors. Okay, that's a big deal. It's a very big deal. Let's see why. Since the band gap of gallium arsenide, and we're going to use gallium arsenide, is 1.44, we would expect the resistivity of pure uncompensated material without any doping, just pure intrinsic, to be extremely high. And I have 10 to the 6th. I thought it was 10 to the 7th. I'm not sure. You can check that out. But anyway, the resistivity is 1 divided by the number density divided by the electronic charge divided by the mobility. I use 10 to the 16th. It's 10 to the 60th. I suppose that's a reasonable number. The electronic charge 1.6 10 to the minus 19th. And here I'm arbitrarily saying that the mobility is about 1,000. That's a little bit on the high side, but look at the number I get. 10 to the 9th ohm centimeters. Huge. That is an insulator. That's like glass. That's really an insulator. Now let's compare the energy band diagrams for the shallow doped compensation on the left side and the deep trap compensation on the right side. On the left side, if I could get it right, which I can't, if I could get it exactly the same, so that I have exactly the same number of donors that I have as electrons, then I would be looking at about 10 to the 10th per cubic centimeter. In this case, for the deep trap case compensation, I have that the number of acceptors is equal to 2 times the number of donors. Remember, we said the number of donors is 10 to the 16th. The number of acceptors is 2 times that. Therefore, the number of electrons in the conduction band is Na divided by 2. And since N is equal to P, we find that the compensated Ni squared is the Ni squared, whatever that would be. In the case of gallium arsenide, it's 10 to the 6th or 10 to the 7th squared divided by 2. So effectively what we've done is we have halved the band gap. It is if we have a band gap for gallium arsenide, which is 1/2 of the original band gap. Instead of 1.45, 1.44, it's 0.72. And if it was silicon and we were using this, and instead of chromium it would be gold, then instead of 1.1 it would be 0.56. Okay, so what does all that mean? Well, 0.72 is about 60 millivolts, 60 milli electron volts, larger than the band gap for germanium. The band gap for germanium, I believe, is 0.67. We add 0.6 to that. pretty close to 0.72. Now, if you work out the intrinsic concentration of germanium, it works out to 10 to the 13th. That number, I believe. I believe that's a correct number. So that we have approximately 1 order of magnitude lower concentration in 1/2 the band gap of gallium arsenide than we have in germanium, about 10 to the 12th. Remember, 60 millivolts per decade. So if we go 60 millivolts less, we would have a larger concentration. Go 60 millivolts greater, we have a lower concentration. So for band gap of 0.72, we would find that the concentration, instead of 10 to the 13th, is 10 to the 12th. And putting all that stuff in, again, assuming that the mobility is 1,000, which I think is very generous, we find 6.3 times 10 to the 3rd ohm centimeters, and that is really an insulator. There's no problem in that being an insulator. Gallium arsenide, which is chrome doped, is semi-insulating. Why do we say semi-insulating? Well, for the same reason we say semiconductor. So semi-insulating, in my case semi-idiotic, but semi-anything you want. So semi-insulating means it's a semiconductor and it's insulating. And why is that good? Because we can basically use the gallium arsenide as a circuit board. We can put lines right on the gallium arsenide. Were it not a semiconductor, any line that we'd put would be shorted. But if it's semi-insulating, I should say, if it's semi-insulating, we can put lines as close to one another as we can, and we can be quite confident that those lines will not short one another out. Now, if we perform a similar analysis using gold, we find that 1/2 the band gap is 0.55, 0.56, doesn't matter. It's about 120 millivolts less than germanium. It's smaller than germanium. Germanium is 0.67. 1/2 of silicon is 0.55, so we would expect 2 orders of magnitude greater concentration. So instead of 10 to the 13th for germanium, we would expect 2 orders of magnitude, or 10 to the 15th, and we find in that case that the resistivity is 6.3 ohm centimeter. Again, these are approximate numbers, but it is 1,000th of the resistivity of semi-insulating gallium arsenide. This is useless as a semi-insulating structure. It is dead short. This is very useful as a semi-insulating structure, and we can make microwave integrated circuits, which we do. Microwave integrated circuits are ubiquitous in gallium arsenide. Okay, so that takes us to the end, and we just have one more clip. Remember that for every positive charge, we have a line emanating from that positive charge, and it keeps going until it finds its negative counterpart. So the thing that popped into my head as soon as I thought about that was from Mozart's Magic Flute, Zauberflute, Papageno finding his Papagena. So we'll end with that, and we'll see you next time.
Mein liebes Weibchen,
nun so sei mein Herzensteufchen,
mein liebes Weibchen, mein liebes Weibchen. Welche Freude wird das sein?
welche Freude wird das sein?
Wenn die Götter uns bedenken,
Wenn die Götter uns bedenken,
unsere liebe Kinder schenken,
unsere liebe Kinder schenken, so liebe kleine
Kinderlein, Kinderlein,
Kinderlein,
Kinderlein, so liebe kleine Kinderlein, so liebe kleine Kinderlein. Erst eine kleine Papageno, Papageno,
Papageno.
Papageno.
Es ist das höchste der Gefühle.
Es ist das höchste der Gefühle. Es ist das höchste der Gefühle.
Es ist das höchste der Gefühle.
Wenn viele sein. Papageno, Papageno, der Eltern Segen werden sein. Papageno, 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 der Eltern Segen werden sein. Eltern Segen werden sein. Eltern Segen werden sein. Papageno, 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 Papageno,